Alright, so we're going to start with number 1. There was one vote for 1. That kind of makes sense. So, this is very similar to the second problem that we did as an example yesterday. Right? Except in this case we have a smaller mass hitting a larger mass, so something with less inertia hitting something with more inertia. And we have that elastic collision again, and then we want to know the speed of the two pucks, the ice puck and just the normal puck, after this elastic collision. So right away should bring up in the Y. Let's see, this is number 1. You should think about things like, make sure you express what momentum is, that a momentum is inertia in motion, that the system is the two pucks that momentum is conserved in the system. I know I'm going kind of fast, but this is the same. This is what we went over yesterday, right? And then the other factor in here is, since it's elastic, that means kinetic energy is conserved in system. And kinetic energy is energy of motion. I think that hits all points. Except, do I need diagrams for this Y? Yes, because I have a system, and I have a before, and I have an after. So, remember, don't be intimidated by my artistic abilities. Let's see, we have our ice puck. We have our ice puck, which we call IP, and we have our normal puck, which we'll call P, and they're going to be separate afterwards. Also, let's see, what does it tell me about them? Moving east, we'll assume east is to the right, and it's positive. Initially at rest, so this one would have momentum IP in that direction. This momentum of this puck to start with would be 0. And then IP has less inertia than P. So after they collide, P will move in this direction. So we'll call that P prime of P. That's that new momentum of P. And because the ice puck has less inertia than P, I'm going to predict that it's going to bounce backwards. If it had more inertia than P, I would predict that it would continue forward. And if it had the same inertia, I'd probably predict that it would stop, and the other one would take off. So I'm going to predict that it's going to move backwards. And nicely in this, I can check right away. So I'm predicting that my puck's going to go east. My puck will move east, and my ice puck is going to move west. Right, ice puck, that way hits it. Everyone, let's see if I'm right. Good. So I kind of was nice. And now I can say that's my complete Y. So I understand what momentum is. I understand that the two pucks of the system. However you express that. So where I want to start here is that momentum is conserved in the system. We're going to start with momentum of the system before equals momentum of the system after. See how far I can get with that. And so there's two bodies in my system beforehand. I'm going to have two terms here. I'd have momentum of the ice puck before plus momentum of the puck before. Then I have my collision, which is my equal sign. And afterwards, I still have two objects. These should all be vectors. Excuse me. Sorry about that. And I have the momentum of the ice puck afterwards plus the momentum of the puck afterwards. So that's my conservation momentum there. And now I can use my fact that momentum is inertia in motion. And so that means the momentum of the ice puck beforehand is the inertia of the ice puck and the velocity of the ice puck. I know the momentum of the puck before, that's 0 kilogram meters per second. Afterwards, I'm still going to have the same inertia of my ice puck. It hasn't changed. But I'm going to have a new velocity of my ice puck. Plus, bless you, the inertia of my puck. And the new velocity of that puck. Make up those individual momentums. At this point, I'm going to substitute in the values that I know. Remember, stop me if going too fast. Inertia of the ice puck is 0.441 kilograms. So I've got 0.441 kilograms. The velocity of my ice puck before the collision, for me it's 3.09 meters per second. I can just leave off that 0, so 9, equals 0.441 kilograms. I don't know the velocity of the ice puck afterwards, right? Inertia of the puck is 0.9 plus 0.945 kilograms, and the velocity of the puck afterwards, I don't know. So I'm kind of stuck at this point. Yep. That would be the inertia of my ice puck, which in my case is 0.441. Same as the first one. The puck hasn't changed, right? Same puck. I know it's hard with ice puck and puck. So I have two variables here in a single equation. I can't really go any further with this one. So this is where I need to use my other fact. That the kinetic energy is conserved in the system. And so I'm going to just go down a little bit here. And the kinetic energy of the system before equals the kinetic energy of the system afterwards. And this is, remember, due to the fact that it's an elastic collision. So, I have two bodies ahead of time. KE of the ice puck plus KE of the puck equals, that's the collision, that KE afterwards of the ice puck and KE, or kinetic energy, afterwards of the puck. Since they're separate bodies, each one has its own kinetic energy. And now I can use my next thing that was in my Y, which was that kinetic energy is energy of motion. And if I look up on my equation sheet, kinetic energy is 1/2 the inertia times the velocity times the speed squared. Remember, this one is the scalar, not the vector. So, substituting in that, for my equation sheet, I'd have 1/2 inertia of the ice puck, speed of the ice puck squared, plus 1/2 inertia of the puck, speed of the puck squared, equals 1/2 inertia of the ice puck, plus the new velocity of the ice puck squared, plus 1/2 inertia of the puck, new velocity of the puck squared. Kind of a scary looking equation. All these tick marks and squares and halves and M's. Anything common in all four of those terms? 1/2. So if I've got something common in every term, what can I do? Take it out. So I'm the halves are just gonna disappear. But that's the only thing that's common, right? Now I need to substitute in. See if there's anything else that'll go away nicely. Is there any of these values that are multiplied together? Are there any of them that might be 0? Yeah, the velocity of the puck before is 0, right? So that means this whole term goes away. So far I've managed to get rid of all the halves. And I've gotten rid of one term, so I'm trying to make it a little, use a little elimination there to make maybe it not as scary looking. So now I'm going to substitute in. The inertia of the ice puck was 0.441 kilograms. Its speed ahead of time was 3.09 meters per second, equals 0.441 kilograms. That inertia of the ice puck again. That I don't know. And this was 0.945. Velocity of the new velocity of the puck. And again, I've hit a stopping point because all the physics basically is done. But now I've hit a stopping point in the math because I've got another equation, but it also has two unknowns. Oh, but wait a minute. Those are the same two unknowns as I had before, right? B IP prime and B P prime. So if I look at these equations together, so if I look at this one, all its weirdness, and this one, the math tells me I have two of the equations with the same two unknowns, so they must be able to be solved. And there's a number of ways you can do that. I'm going to do it using Wolfram. Okay? I'm going to use the computer to do it because while the algebra might be interesting to some people, I'd rather just be able to get the algebra done. So, to enter them into Wolfram, I want to make my life a little easier, and I'm going to make my variables x and y rather than VIP and VI and VP. So, what I'm doing down here, going to red, is I'm saying x is the same as VIP prime, and y is my VP prime. So I'm going to make them so they're simpler to type in. All right? I'm going to rewrite these two equations in terms of x and y. So this first one is going to be 0.441 times 3.09. Since this is just math doesn't really need units, times 0.441x plus 0.945y. That's that blue one. put into X and Y. Now let's do the same thing here. 0.441 times 3.09 squared equals 0.441 x squared plus 0.945 y squared. So there are my two equations. Now I can do this with my calculator. I can also do it by, say, solving that first one for x and substituting it in for x in the second one. I could graph and look for intersects. There's lots of different ways I could do this. I'm going to go up to physics is fun and go down to the bottom, and I could put it into either one. But I'm going to use Wolfram just out of personal preference. And let's see, I'm going to pull up my curtain so I can see. Here we go. So I'm putting in 0.441 times 3 point, oops, I'm going to make this a little bigger. Times 3.09 equals 0.441 times x plus 0.945 times y. Now, I need to put in a second equation. I do comma, another space, and I put in my second equation, and it will solve the two simultaneously. That times 3.09 caret 2 to make it squared equals 0.441 times x caret 2 plus 0.945 times y caret 2. Hopefully I entered everything correctly. And it gave me two sets of answers. And the one that makes more sense for me is this first one, because I predicted that the ice puck would bounce backwards. So I should be able to just enter these and say, okay, the velocity of the ice puck afterwards is negative 1.12 meters per second, and the velocity of the puck afterwards is 1.97 afterwards. I'm wondering, did it ask for velocity? Let's see, it asked for just the speed. So where I know the negative indicates direction, for the ice puck I'm going to put in 1.12. And the speed of the puck, that was 1.97. Cross my field. Okay. Any questions on any part of that one that I can answer for you or show you? Yes, Lynn? The answer should pop up. Okay, so you put it in here, put in everything, right? When you scroll down, you should get a box that says solutions here. That means you probably entered something wrong. I'm going to look at yours. Or have Dave, maybe have Dave look at it. We'll look at each other, see if you made offsetting mistakes, and I'll come over and look at it. Okay, but that's my guess is that, all right, so in number 3, what type of collision is it? Elastic or inelastic or semi-elastic? Okay, why do you say semi-elastic? So what would you like the words best? Cannonball's hard. Well, remember, the type of collision is based on what the objects do, not like if they're hard, soft, or pretty. If it's elastic, they're going to bounce off each other, and the kinetic energy will be semi-elastic, they're going to bounce off each other, but kinetic energy won't be conserved. And inelastic, they're going to stick together. So this one, as you point out, is inelastic because they stick together. Before the collision, you have two objects, the elderly performer and the cannonball. After the collision, you have one object, the elderly cannonball. And hopefully they become two objects later, but, all right. So this is an inelastic collision. Okay, so again, I would start off in my Y with making sure that I understand momentum is, motion of inertia or something like that. Spelled it right. Motion of inertia, that the system is the EP, elderly performer, and cannonball CB. Momentum is conserved in system. Do you need diagrams for this one? Well, ask yourself, is there a system? Yes. Is there a before and after situation? Yes. The answer yes to those two questions. You need diagrams. So I could actually, in my Y, explain things like, there's two bodies in the system beforehand. There's only one afterwards. For me, I'd rather show that in the diagram. So let's see. I've got my elderly performer, his arms out, or her arms out, and our cannonball. And afterwards, we have the elderly performer with the cannonball. That's a good art. I'm going to have to save that. Let's see, the cannonball is this, horizontal is this. I'm assuming he stands there and catches it, right? So I'm going to say the momentum of the elderly performer beforehand is 0, and this will be the momentum of the cannonball beforehand. And then afterwards, they're going to have a momentum in this direction, and we're calling that the elderly cannonball, right? So that would be my momentum diagrams to get that I need for my Y. Any questions on the Y before we move on to the how? No? Good? Alrighty. So, I'm going to start with my momentum of the system is conserved. Nicely, everything is moving in one direction, so I can call everything positive. So beforehand, I have two objects. I've got my cannonball, and I have my elderly performer, which both have. And afterwards, I only have one object, my elderly cannonball. So, and that's one reason I like the diagram. I mean, I drew two objects before and one object afterwards, so I look at my equation here, and I have to have two terms before and one term after. Okay, so I kind of, visually, I like that lining up for me. And then I'm going to use the fact that I understand what momentum is inertia of the cannonball, velocity of the cannonball, plus, oh, what's the momentum of the elderly performer? 0, right? Don't forget my units so I don't give away any points. And then afterwards I have the inertia of the elderly cannonball and the velocity of the elderly cannonball afterwards. And, well, I think I know most of those values. Let's see. Inertia of the cannonball. 27 kilograms. 27 kilograms. Velocity of the cannonball. For me, it's 10 meters per second. Inertia of the elderly performer and the cannonball together. Our elderly cannonball, well, that's going to be the inertia of the performer plus the inertia of the cannonball. So I've got a 65 kilogram performer and my 27, so I've got 27 kilograms plus 65 kilograms. They've joined together. And then the velocity of the elderly cannonball, which is what I'm looking for. So yay, one equation, one variable, the rest are numbers, solved. Right? Any clarifications, questions on that? No, we're good? All right, I'll come around and help you individually. All right, so we have about 10 minutes. I thought I'd spend a couple minutes looking at number 2. It's very similar to number 1, which we did. And because you have another elastic collision, this time, though, they give you slightly different pieces of information. Again, they tell you it's elastic, so you know momentum and kinetic energy are both conserved. So the setup is very similar to 1, except this time rather than telling you the inertia of each body, they tell you the inertia of one of them, its initial velocity, and then its velocity afterwards. And they ask you to find the velocity of the target ball and the mass of the target ball. The one thing to be careful of here is that notice afterwards the incoming softball bounces backwards with the speed of this, meaning that in the momentum equation, you've got to enter that 1.9 as negative 1.9 because it's coming back. So that's the main thing to be careful there with number 2. But it's very similar setup to number 1. Same ideas here. If you have an elastic collision, so your momentum and your kinetic energy are both conserved. And just be careful with your sign to make sure that you use this 1.9 meters per second as negative in your momentum. Of course, in your kinetic energy, either way you look at it, it's just the speed, so it's just 1.9. Or you can think of it as, well, what do you get when you square negative 1.9? You get a positive value. Okay? So you can think about it either way. 5 is also very similar in that you have the same type of situation, even more similar to 1, just giving it in terms of a car and a truck. Be careful, as with all of these, when you enter them in, make sure you enter in for the correct one. You know, the velocity of the car in for where it wants the car. It does ask for the speed, so you shouldn't have to worry about positive or negative in your answers. Make them both positive. So it asks for speed, not velocity. All right? So let me know if you need help individually on those. And don't forget, 4 has that tutorial feature that will help you work through it if you have any questions on number 4.